Hi guys, happy Friday. It is time for us to talk about chemical reactions and writing and balancing chemical equations. So this first part will be about chemical reactions. Okay. So a chemical reaction is a process in which bonds are broken and remade to create different substances than what we started with. So we have one or more reactants, and then we end up with one or more products. So for example, methane, this is methane, plus 2 oxygens will give us 1 carbon dioxide and 2 waters. And I like this because this gives us a molecular view, but it also shows how it's written in terms of formulas. So CH4 plus 2 O2 will give us 1 CO2 and 2 waters. Excuse me, so sleepy. What are the different types of chemical reactions? There's many different types of chemical reactions. The 5 that we're going to encounter in this class are composition, decomposition, double replacement, which I like to call partner swap, and that's what we've done in all of our labs with the little drops, our double replacement. We'll look at acid-base reactions and also combustion reactions. So there's some specific ways that we notate things in chemical reactions and in writing chemical equations. So we put a little s in parentheses if something is a solid. So in this case, this is a little chunk of solid O2, which is super weird that they picked that as an example, but whatever. So it keeps its shape. The molecules are not moving very much. That's a solid. Liquid molecules are moving more, and they have a little more space in between them. We do lowercase l in parentheses. Gas, lots of space between molecules, huge movement, when we notate that with a parentheses G. And we're really familiar with those 3 phases of matter. If we look to the far right, though, we have this state that we call aqueous. And aqueous means that something is dissolved in water. So this example is showing chlorine ions and sodium ions dissolved in water. So this to our eye would look just exactly like normal liquid water that's pure, but there's actually all these ions dissolved in it. So a little more detail on that. Aqueous compounds dissolved in water, such as polar covalent compounds or salts. Water dissolves things through interactions with its polar oxygen and its positive hydrogen end, and so it needs to have some type of positive and negative to interact with. Salt is just an ionic compound that dissociates, so it breaks into 2 pieces or more when it's dissolved in water. And so the example here is solid sodium chloride is put into pure liquid water. So it's being shown on the large scale in A. And then B is the molecular view of the salt crystal, the solid salt, before it goes into the water. And then we would notate that as being NaCl aqueous, AQ. And that really means that we have sodium 1 plus and Cl1 minus dissolved in liquid water. All right, so next we're going to look at each type of reaction, and I'm going to give you the general form and the example of each one. So composition is when things get stuck together to make something new. So this is like element A, element B, they react and they make some molecule. Most examples will look like two elements combining to make a compound. So an example of that is when hydrogen gas and oxygen gas react and they make water. And that's actually what they use for rocket fuel, is a mixture of hydrogen gas and oxygen gas. And that is a really, really powerful exothermic reaction. That is a composition reaction. Decomposition reactions are the opposite. So basically the reactant, which is some type of compound, breaks into two or more simpler products. And so that looks like this. So you have compound AB, and it breaks apart into atom A, or element A, and element B. So compound, element 1, and element 2. Some examples include explosions, and they can be really complex. So for example, ammonium nitrate, which is like fertilizer, right? That's a solid. And if you give it just a little bit of energy to start its reaction, it goes crazy, and it makes nitrogen gas, N2, it makes hydrogen gas, H2O, and it makes oxygen gas, O2, and it's very exothermic. It makes a lot of heat, and because it's so hot, these gases expand very, very rapidly, and that's what creates the explosion, is that displacement. A simpler example, though, would be something that's just breaking down into its elements. So liquid water can be broken down into hydrogen gas and oxygen gas just simply through running an electric current through it. It'll split it in part, and you'll get hydrogen gas and oxygen gas. Double replacement reactions are what we focus on the most in this class. And this is when the cations of two compounds switch places. And usually this takes place in solution, which is what we've experienced with our little solutions in those pipettes. The general form is A, so A is a cation, X is its anion, and then B is a different cation and a different anion, and then they switch places. So instead of AX, the product becomes BX plus AY. And these only happen if one of the products is a precipitate, so solid, a gas, or a new covalent compound. So we have already talked about precipitates a lot because we've worked with them, but they're just an insoluble solid that is the result of mixing the solutions. And insoluble means it doesn't dissolve in water. So you either see some type of precipitate form, you see bubbles, that indicates that there's a chemical reaction, or a new covalent compound might form, and that sometimes is tricky to observe. And so we haven't really focused on that in class, and that's okay. So here are some beautiful little examples. If we have an aqueous ionic compound plus an aqueous ionic compound, we'll get a precipitate. And so an example of this is sodium chloride mixed with silver nitrate. You get sodium nitrate and silver chloride, which is solid. And the pictures are showing a number of different precipitation reactions between ionic aqueous solutions. You should definitely recognize this beautiful yellow one. We've done this reaction quite a few times with lead, and it just makes such a pretty yellow precipitate. It's just delightful. Okay, acid-base reactions. We've talked a little bit about acids, right? They're substances that produce hydrogen plus when they get dissolved in water. So hydrochloric acid, carbonic acid, we talked about this a lot in naming. Base is a substance that produces an OH minus when dissolved in water. So it produces hydroxide. Some examples of that are sodium hydroxide, potassium hydroxide, things that have hydroxide in them. Weird. Yeah, so that's a base. In an acid-base reaction, what happens is the acid and base react with each other and they make water and some type of ionic compound, which we just call a salt. And this is really just a glorified partner swap reaction. So if you mix hydrochloric acid with sodium hydroxide, both of those are very dangerous in solution. If they're in a high concentration, they can really mess up your skin. And if you mix them together, though, they just turn into water and sodium chloride, common table salt. And, you know, this is like a favorite trick of old chemistry professors. They would love to take an acid and a base and they mix them together and then they drink the salt water to be like, see, it's neutralized, it's safe. I'm like, that's a goofy thing to do. But anyway, it should be, theoretically, it should be safe. But you shouldn't drink salt water, it's not good for you. Last type of reaction is a combustion reaction. These are the funnest reactions that we're not really allowed to do. Products are always CO2 and H2O if it's combustion. So if you see something that spits out CO2 and H2O, you're like, that's combustion, boom. And interestingly, for those of you who are biology minded, cellular respiration makes CO2 and H2O. And cellular respiration is basically a combustion reaction that your cells are doing on a really, really tiny scale, which I think is cool. But, you know, whatever. Exothermic process, it creates heat. And the general form is a hydrocarbon, so hydro meaning hydrogen, carbon meaning carbon, plus oxygen gas, so O2, and it makes carbon dioxide and water every stinking time, carbon dioxide and water. Okay, so I've represented this hydrocarbon as CXHY, and the X and Y can be really any number that creates a stable molecule, right? So there's C2H2, there's CH4, there's C3H8, like there's lots of combinations. Yeah, so that mixes with the oxygen, you get carbon dioxide and some heat, and you know, good times. So here is a really specific example. This is propane, C3H8. So if you have a propane grill or a gas stove or anything like that, this is what you're dealing with. And so C3H8 plus O2 gives us carbon dioxide and water. And so on the left, we have a controlled propane burner that's burning. On the right, we have an uncontrolled propane fire that is a giant propane tank. These are common in rural areas where they don't necessarily have like electricity, like lots of electricity coming to the house, or they don't have like gas lines to the house because they're like in the middle of nowhere, so they run off of propane. Yeah, very flammable, combustible stuff. Thanks. So then how do we turn the English into a chemical equation? Because sometimes we write equations using our words and not the symbols. So if we want to do that, we're going to look at this example when a solution of lead 2 nitrate is combined with a solution of sodium carbonate, precipitate forms. Write a chemical equation to represent this reaction and indicate the states of the products. We're going to have to do that in part 2 because we are out of time.